Okay, let's begin. Let's begin. What are we going to talk about today? Yeah, all right. We saw the film, Relativistic Time Dilation. Okay? Steve Smith did all the drawings. I told you Steve Smith was a dishwasher. And after submitting the film to the American Educational Film Festival in 1977 and copping first prize, boom, Steve then advanced to the status of taxi driver. Yeah. The arts. Very rewarding, gang. Why is it Mommy and Daddy get disappointed when you say you want to be an art major, right? With the prices of housing going up, you say you want to be an art major. Well, on the film, we saw where time seemed to be different for people traveling and time was different for people at rest. It turned out the speed of travel for that particular case, where we go from 2 hours to 2.5 hours, was 60% the speed of light. You saw the film that kind of got into all this stuff about counting flashes and all that sort of thing. Would you like to see that nice and succinct, so there's no question? So when you look at what I'm going to put on the board, boom, it all makes sense. Time dilation comes alive. Would you like to see that?
Yeah.
I can do that for you right on that empty part of the board. Would you like to see it? Never mind the talk, never mind the rhetoric. Let's get to it, huh? Here's time dilation. Hey, all right, huh? Does that do it for you? Yep. Hey. Now, what's that mean? This is derived in the footnote of your textbook. Is that not true? Simple Pythagorean theorem, right? Geometry, okay? Won't go through the derivation now. But it just states that the time, the funny business time, the time that one will experience due to relativistic effects, meaning really motion effects, huh? The time that one will experience will have to do with the time that one would experience if there were no motion at all, t sub 0. But modified by the square root of 1 minus v squared over c squared. V is the relative speed between that being observed and that observing. That's important. Very important. This V, to understand what that means, the nature of what that V is at the root of a lot of misconceptions about relativity. Again, V stands for the velocity between the observed and the observer. Let me give you an example. If I put numbers in like this, 87% the speed of light, I put in a 0.87 c, and do that, it turns out my time will be twice. I'll observe things take twice as long a time, okay? Now, let's suppose I travel, relative to you guys, at 87% the speed of light. And as you guys watch my watch undergo its second-hand thing, you guys will see my watch taking twice as long to make one complete turn. You hear what I'm saying? You'll see it stretched out by 2. Now, travel with me, and we'll watch. Now, we're going 87% the speed of light, you and I together. You look at my watch. Do you see any funny business? What's V? 0. Because the observed, the watch, the observer, there is no relative speed between the observer and the observed. Get it? So you in the rocket ship notice nothing unusual. If you travel along with the watch, then V is 0 in this equation. And if V is 0, then this term is 0. What's 1 take away 0? 1. What's the square root of 1? 1. And how do your times compare? There's no difference. Time, my time, your time, same. Okay? So that's very important to understand what that V is. Now, in our particular case, V, for this example, was 60% the speed of light. Let's see what happens when we put that in there. It was a 2-hour trip with no funny business. Now, 6 times 6, 0.36. And the c square and the c square cancel out. So it's 1 minus 0.36. Does anyone know what that is? Okay, it's going to be 64, huh? 1 minus that is going to be 0.64. But now you got to know the square root of 0.64. You know the square root of 64? 88, 64? What about 0.64? It's 0.8. Now you got to know how many times does 8/10 go into 2? See? Calculator types? Well, I'll tell you, I've done it before. 2.5. Yeah, 0.8 will go into 2.5 times. Yeah. So you know what? The time that the Earth type C is the 2 hours that they would see if the velocity were 0, t sub naught, t sub 0. The time the Earth type C is at 2 hours, but modified by this thing over here. It's called the Lorentz-Fitzgerald contraction factor, all right? And that v is the speed, the relative speed, and c, of course, the speed of light. And we've done that, we find out that, wow, a 2-hour trip appears to be 2.5 hours. And that's what we saw in the film. Now, if you go at higher speeds, the time dilation means stretched out, huh? The stretch out of time is even more. If you went 87% the speed of light, and I'm not going to take the time to do that now, but if I put a 0.87 in here, I would come out over here where the time is twice as much. Twice as much time, see? So 2 hours would be 4-hour trip. And if I went 99.5% the speed of light, that fast, then it turns out the time would be 10 times as much. So a 2-hour trip would look like 20 hours. Let's take the extreme case. What if I went at the speed of light itself? Okay. Then this would be just c, not a fraction of c, but c. And c squared, what? That's 1. What's 1 take away 1, gang? 0. What's the square root of 0? 0. How many times does 0 go into any number? I mean, think of 0 as being something tiny, okay? How many times does something tiny go into something big? Infinite. So it turns out as the speed of light, if something gets up to the speed of light, time becomes like infinite. Take an infinite time for that 2 hours to go by. We talked about this before. Time would be frozen. You would see time frozen. So, at everyday speeds. How about speeds like you when you walk down the street? Does time dilation occur when you walk down the street? I should have asked this in the quiz, yeah? Does any time dilation occur when you walk down the street and your friend sits on the curb? A lot or a little? A little. But it's happening. See? Some people think that the effects of relativity only occur beyond some particular speed. That's not true. They occur at everyday speeds, but the effects are negligible, small enough to be neglected. See? So, I mean, if you put like this, your speed in here, put the speed of something moving, okay? How fast does the space shuttle move? What is it? Maybe like 1,000th the speed of light, okay? Even less than that, okay? So you got 0.001, and then square that, and it becomes, you pretty much get the 2 hours. When these astronaut type go up and they go around, round, they come back down, they're not even a second different in time. Not even 1 second. Because their speeds are trivial compared to the speed of light. But it's there. It's only for very, very high speeds that the effect becomes apparent. And those speeds we don't deal with in the everyday world, so it's not common sense to us. Maybe in tomorrow's world, when we goose up to speeds like that, it will be. I'll give you an example. When you go to the travel agents today, you see these exotic posters on their walls, right? They get posters of the Hawaiian Islands, right? And everyone wants to spend a little time in the Hawaiian Islands, right? So they put these posters of the Hawaiian Islands with the palm trees and all that, the Royal Hawaiian Hotel and all the pink, and it just makes you want to get a couple of weeks off and go there, doesn't it, right? Anyway, you see these posters of places. How many posters have you ever seen in a travel agent that posts times? Like, you can talk about traveling to South America, you can talk about traveling to the mainland, you can talk about traveling to Europe, but can you go to the travel agent today and talk about traveling into time? We got a New Year's coming up. We got a big one pretty soon, huh? 2000, the year 2000, okay? And then 2001, 21st century, yeah? How about someone says, well, I'm not so much interested in that, I'm kind of a futurist. Most of my friends are sort of like historians. They study history, where we've been. And it's kind of a real gas to know where we've been and where we are now. But my bit is, where are we going? That's what I'm interested in. And what I'd like to do is I'd like to travel to the 25th century. And I'd like to see what human beings are doing for New Year's Eve in the year 25,000. Okay? 2,500. 2,500. Okay. 2,500. What's it going to be like then? Now, you go to your travel agent now and ask. You know what they're going to say to you? The same thing they would have said to you a century ago if you told them you wanted to go from one part to the other part of the world in a metal airplane. They'd say, come on, you got to be, oh, come on, you can't fly. Metal's too heavy. But we can fly today. Tomorrow we might be century hopping, my friends, century hopping. You might go into the travel agency and say, hey, I want to visit the year 2500. And you take that trip. But the travel agent says, oh, if you want to go that far ahead in time, that's going to take you 3 months. That's a 3-month trip because our rocket, this particular rocket, the Alpha rocket, will take a 3-month trip. What are you going to do for 3 months? And you say, well, I'm going to bring along my reading, right? And so you'll be properly entertained for 3 months. And you take your 3-month trip. You come back to the Earth. Maybe it's 2,500. Can you do that today? Can't do it today. Don't have the technology. Tomorrow? Maybe not. Maybe so. Who knows? These ideas right now are far-fetched. But I'll tell you one thing. When you travel through space, you travel through time. And some people think it's like outer space, like there's something magic about outer space. Okay? Let's suppose someone says to you, hey, I wonder what it's like in outer space. What is it like in outer space, gang? Guess who's there already? We are. We are in. The Earth is in outer space. In control or out of control? Completely out of control. And the Earth is just hurling through space. Anytime we could hit a bunch of meteors and you know what happened to the dinosaurs a few years ago? At any time. I don't want to arouse your paranoia, but the Earth is in outer space. It's been in outer space all the time. And we are space creatures. We are in outer space. And some people think that all these ideas of relativity have to do with that space out there. That's not true. You could take the space of this room. A little scenario. Let's suppose in this room we had a centrifuge. And that centrifuge whirl around, round, round. And you guys stand outside. And some people in the centrifuge whirling around. Is there any speed relative to you for them? Yeah, there's a speed, okay? There's a speed. This V in the equation would have some value. Let's suppose you got in a centrifuge like that. Let's suppose you did something like this. You're in the centrifuge, you're sitting down, they belt you in, okay? You're all belted in. And this thing is part of the rim right here. It's going to whirl around, round, round. Now, what would happen if you sat in a chair like that, belted in, the back, of course, for your head, you don't, your neck to break you. What would happen if they goosed it up to you're going like speeds near the speed of light? Would you be comfortable or a little bit nauseous? Honey, you would be dead, okay? You'd be splattered all over that thing, right? Centrifugal force, okay? You'd be splattered, you wouldn't make it. You wouldn't make it. The accelerations would be too enormous. But let's make believe you could sit in the centrifuge and go up to the speeds near the speed of light without getting killed. Just make believe, okay? What might happen? It might go like this. They say to you, okay, here's a little red button down here. Now, when you get tired, for any reason you want us to stop, hit the red button. Outside, the alarm will sound. And when the alarm sounds, we'll cut down the electricity and bring it down to a stop, open it up, and see how you're doing. You're the first one to try this, so good luck. So they go out, they close the door, they got you belted in. You feel that thing vibrating, right? You're picking up speed, and you say, this thing's really going, okay? And you say, oh, about 10 minutes, I'm getting bored. I want to get out and read my physics book. I left my physics book outside. You hit the red button. Outside, an alarm, okay? They take the bit, pull down the switch, the electricity stops. Door opens up. Someone looks in and says, what have you been eating for the last 3 months? How did you go to the bathroom? You've been belted in. What have you been doing for 3? How come you waited so long before you hit the button, man? You say, for you, it's a few minutes. But for them, 3 months. This happens with radioactive decay. Measure the radioactive decay rate of a mineral. Now have the mineral move relative to the counter. Ooh, the decay rate changes. These ideas are solid, gang. Some people ask, what would happen if you travel faster than the speed of light. Could you do that? As we understand relativity, we say, no, you can't do that. Hyperspace and Star Wars notwithstanding. You can't go faster than the speed of light. But what if you could, is oftentimes the question. And it turns out to be that if you could, it'd be kind of bizarre. Would you like to see what I'm saying? Let's suppose you did this. Let's suppose you're on this planet, the Earth, and you want to jump to another planet. And you're going to travel between planets at a speed greater than light. Now, you can't do that. But let's make believe. And let's suppose up on this other planet here, you have a tripod all set up, and you can stand there and look through and look right down through the path. And here you are down here. You're in front of a great big clock like Einstein had in his village square. And what you do is you jump, you say, boom, Shazam, okay? Boom, all of a sudden you become super or something, okay? And you fly up here. Well, here you go on your trip when you jump up. First you get here. Then you're here. Then you're here. And then all of a sudden, boom, you're up here, okay? Boom. What would a trip like that be like? Okay. Let me ask you a question. What would you or who would you see in the telescope? Think about that. Who would you see? What would you see? If you could go faster than light, Now, I know you can't do that, Lee. But let's make believe. Let's make believe. If you could go faster than light, and you took a look here, who would you see? Yourself. The most important person in all the universe, yourself. I'm kidding about that, okay? But you'd see yourself. Now, would you see yourself like this? Shazam! You see yourself coming closer, 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 and all, you're all together. Would you see that? And speaking with an N. You'd see something more weird than that. Much more weird. Let me give you a hint. First of all, you're here. Later on, you get to there. And after that, you get to here. So yes, you would see yourself. But would you see yourself at position 1, then 2, then 3? You're going faster than a light that's bouncing off you. What would it be, gang? Check your neighbor and see if your neighbor has any idea what's going on. How are you going to see yourself? You're going to see 1, 2, 3? How many people say, no, I think you're going to see 3, 2, 1? Let's suppose when you made that jump, you got a watch, you got a great big one, big Mickey Mouse job, okay, and you put it right here, a great big giant one, okay, you've seen those ones, okay, in the fun shops? And you got that watch and you go up like that. So you can look at the watch that you're wearing on your wrist. Let me ask you a question. Which way is that watch going to be reading? Forward in time or backward in time? Begin with a what? B. You see that? You're going to see yourself going back down. You'll see yourself here, and then here, and then here. Because you got up there faster than light. And so that light coming to you. So you see yourself going backward. I got another question for you. When you're looking at the clock in the background all the time is the clock with a great big hand, yeah? How are you seeing that time going? Clockwise, regular or backward? Well, let me ask you guys a question. If you just get out here and look at a telescope, and there's no motion between you and this clock down here, are you going to see that clock just moving as regular? How many say yes? Oh, you guys don't know that. Well, let me ask you this question here. If you stand on a tower outside and you got a spyglass and you go look at a clock downtown, is that clock going to do something funny? All right, let's suppose you get another planet and you look at the clock downtown. Is it going to do something funny? How many say, hey, it'll run just like it always runs? At the wrong time. Well, not everybody. Okay. Well, let me just tell you, yeah, nothing's funny. It's only when you're moving, okay, when you're moving. So what you'd see here is you see the clock here running backward, and back here you'd see the clock running forward. So on one eyeball full, you'd see time going backward and forward. Bizarro. Lee?
Now, it's the you that's on the planet that's seeing this. There are two yous. There's a you that's flying through space, and there's a you that's on the planet.
Yes.
And when I was answering your question first, it seemed to me that if you were looking behind you, you'd be, or if you were looking ahead of you, their light wouldn't have reached the telescope before you got to the planet. if it's the you that's flying through space. It's the you that's on the planet that sees the you.
See,
coming
Lee,
in.
you get up here at the telescope
And then you
before
wait.
this light gets to you.
Right.
See, because you've gone faster than light.
So
You
that's
get up
you
here
over
first.
there, and you're standing waiting for yourself.
You're waiting for the light to get to you.
Yeah.
And all we're saying is this light will get to you first because it's closer. And this light will get to you later because it's further away, and so on. So you'll really see yourself going backward in time. Now, how long will this backward sequence last? Will it last like, could you see yourself going backward? You land, boom, you start walking backwards, you get in your car, you drive back. You keep watching patiently. And you see yourself when you're going to college at UH, remember that? Okay. Then you see yourself when you're in high school. And you keep watching backward. You see yourself when you're a little kid. See yourself when you're born. See yourself as you're being born. Or see yourself before you're born, you know? You know, come on. Would you see that?
You're not going the speed of light then.
Yeah. Would you see all these things, gang? Could you be patient and keep watching time go backward, backward, backward? Answer begin with a... No, you couldn't. Okay. The show would be over after this gets to you. It's like if I shake a stick in the water and run out here and wait till the waves come. They don't keep coming forever and ever and ever. Okay, it went from the time I started shaking the stick or the time I jumped from here to here. In fact, here's the thing, too. Everyone take a look at their own hand. Put your hand right there. Are you guys looking at your hand as it is right now? No. You're all the time looking in the past. Because light left your hand and it took some time to get to you. So you're seeing your hand as it used to be. You're seeing me as I used to be. I'm seeing as you used to be. We're all looking at history. Now, how much? Okay. This makes sense when you talk about big distances. Big distances. Let's suppose you could go faster than the speed of light, come way out, and then watch events on the Earth. Wouldn't you see them a long time ago? You know? Let's suppose you got out like 2,000 light years away. 2,000 light years away. Right now, hit, boom! Instantaneously, you're out in the universe 2,000 light years away from the Earth, looking at the Earth. What do the calendars say? They say like 0, yeah? Well, of course, they made the calendar thing later on. Right? Let's suppose it's like 25. Then you see the calendars like, you know, BC, right? You see someone's calendar might be something like this. Hanging on the wall, right? Okay. Were there ever calendars at the... Come on. Okay. How did they know? Right? Okay. Okay. No, but the point is, if you could get way, way out there, you could see the Earth. You could see the Earth 2,000 years ago. Paul.
Is that same type theory that you're talking about when they say that the space telescope is going to launch on the shuttle is going to be able to look back closer toward the Big Bang than we can now?
Yes, we're looking in the past. Yes, yes. When you can look out, when you guys know this. When you look at the stars, you know the stars might not even be there. You know that. And the closest star is what? What's the closest star? It's our favorite, the sun. And the sun's 8 light minutes away. It takes 8 minutes for light to get to us. The next nearest star, Alpha Centauri, looks like a proper star, right? What do you think our star would look like if you get further away? What's our star look like from Pluto? Our sun from Pluto looks like all the other stars. So all the stars are, but you're looking at them in the past. See? Now, anyone out there looking at us right now is looking at us in the past. No one can see us right now. I mean, like I said, didn't you have trouble seeing your hand? Hey, I'm not sure that was my... I'm exaggerating there. But yeah, they have this thing. But let me just short circuit things and ask this gang. Let's suppose someone was kind enough to put a mirror way out on a planet. And make it so it's pointing right down to us. And it's 1,000 light years away. You know what I'm talking about, 1,000 light years? It takes 1,000 years for light to go up there. Or it takes 1,000 years for light to go down here. Now, sometimes you guys in the morning, you get up and you brush your teeth. Why do you guys look at the mirror when you're brushing your teeth, by the way? You ever notice that? You brush your teeth, you look in the mirror, yeah? Okay. Or you're combing your hair, you look in the mirror, right? Okay. When you look in the mirror, you see yourself almost at the same time, right? Now, what if the mirror gets farther away? Farther away, farther away. You know, you start to comb your hair and you have to wait a little while. And then you see, okay. Isn't that true? Okay. Well, let's suppose this mirror is 1,000 light years away. And you're over here and you're combing your hair. How long do you have to wait to see yourself? 2,000 years. But let's suppose you're not interested in seeing yourself. You're interested in seeing where you came from. And you just take a plain old look in the mirror. And you see the Earth. You see the Earth at what time? You see the Earth 2,000 years ago. And if you could really resolve that and get a clear image, you would really see what the Earth looked. Never mind the books. Never mind the carbon dating. Never mind all the records. Honey, you just look and you'd see it. Now, has anyone put a mirror up there for us? Haven't found any mirrors yet. But here's some speculation. I wonder maybe just matter in the universe might be able to reflect, and the image might be there. Maybe in the future we can do such things. Kind of blurry, but who knows? At this point, nothing much surprises me. Another effect of relativity, of high speeds, is the increase in momentum of things, but more than the speed would dictate. It appears that the mass itself, the mass of an object itself, increases with speed. And we have a relation for that, and that relation is this. Would you guys like to have a real rush? A real rush? By that I mean, you know how sometimes you go out and you see a sunset, and you look at the sunset, and the sunset is so beautiful, and you're with a friend, and you just get this rush. Oh, where you just feel so good. It is one of those feelings you're glad you're alive, yeah? Or you hear the proper music, and you just, it just does it to you, right? There's sometimes something will happen, and just, and just so, Would you like to have that experience today in this classroom? And you go home tonight and say, Mom and Dad, man, I got a rush in class today. What that dude did in that board was more beautiful than anything I can remember ever seeing in my life. Would you like to see that? Would you like to have that kind of a rush, that kind of an emotional high? Would you like to have that? I can do it for you right there. I'm going to give you all the relativity equations in one part of the board. Watch this. Yeah. Gaze. Gaze. Now, I know what you guys are feeling. But let me tell you the difference between you guys and other people. If a janitor walked in here, the janitor would just look at that and think nothing of it and walk right by. But when you guys look at that, don't you, how beautiful, how beautiful. Is there anyone here that does not feel that feeling? Everybody? Only one? Only two? Does that do it for you guys? Huh? There it is. There's all the relativity right there. It turns out that the mass of things will become more with speed. It turns out when this Lorentz factor is down below, it's going to make the quantity always bigger. This will always be less than 1. So something less than 1 divided into something will make this bigger. So it turns out the time always gets stretched out. The mass always becomes more, but the length of things becomes less and things contract. And when you put these things all together, you get the equation of the 20th century, E equals mc squared, which tells us that that which we call energy and that which we call mass, two sides of the same coin. If you go to Stanford, California, you'll see the Stanford Linear Accelerator. You're driving down the freeway 280, and there's a great big, long concrete tube, 2 miles long. And in that concrete 2-mile-long tube, they fire electrons. And these electrons go right down a vacuum pipe. Got to get all the air away. You don't want these electrons to get obstructed. And they'll fire for 2 miles down that tube. And when they get to the end, boom, they smatter into particles of matter, and they smash it all apart, and they take a look to see what it's made of. For example, if I want to know what this watch is made of, the one way to find out what this watch is made of is to take the watch, find a concrete wall, take that watch and throw it as fast as I can. And when it splatters, take some pictures quick. And that way I can find out what's inside. Does that make sense? Well, that's what the physicists do. They do that with atomic atoms. And they smash them apart, and they see all the debris. They take photographs, and they got it. Well, that's what the people do at this Stanford Linear Accelerator. Well, it turns out those particles are electrons, the electrons that are shot in your TV tubes, huh? Same old electrons. And those electrons are going 99.99913 the speed of light by the time they hit the target at the end. Honey, they are going fast. But let me tell you something else kind of neat. Those electrons in the first couple of feet are going more than 99% the light, speed of light right there. And they're pushed all the way down. Push, 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 push. The copper wires feeding that accelerator are thicker than your wrist. Enormous amperage, enormous power. And that is put into driving that accelerator. And that energy takes little tiny electrons. You know how light they are, my goodness. Huh? It pushes, 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 pushes for 2 miles. And as they're pushing, 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 it doesn't gain much speed. But it gains something else. It gains momentum without gaining much speed. And what's that imply about the mass? That the mass is becoming enormous. When these things get down to the end, they land with, or they hit with thousands of times more mass than they started with. And so all this energy you're pumping in, all that energy, that energy is going into mass. And how much? Given by this relationship. So at the end of the tube, you'll have more mass than you had when you started, because you're energizing it all the time. And as you push things, but some people say, how come you can't go faster than the speed of light? Well, to go faster than the speed of light, if you got to push, you got to push, you got to push. Huh? When you want to accelerate something, there are 2 factors involved. Some of you people know what the 2 factors involved are. If someone said to you, hey, you're physics type, huh? I understand that acceleration involves 2 ideas. What are those ideas? And you would say, how hard you push, force, compared to how much inertia you have, mass. Isn't that right? It's a force per mass. Now, as you're pushing faster and faster and faster, and the mass becomes more and more and more, what happens at the speed of light? At the speed of light, what would the mass be? See this little piece of chalk? What's the mass of this piece of chalk if I push it to the speed of light? I can use this equation to guide me. If v is the speed of light, zero, infinity. This mass would be pushed to be infinite. Now someone says, now that it has an infinite mass, which means an infinite resistance to any further change in motion, now someone says, could you push it in hyperdrive, honey? Hyperdrive? I've got an infinite resistance to any change in motion now. And so we find out in the universe as we understand it in the 20th century, you can't do that, at least with material particles. There's a speed limit, the speed of light. So you get that cutting you down. One of the important parts of relativity is this. Before we understood relativity, we understood that the human race, no matter how sophisticated they became, couldn't travel very far in space, and the reason's simple enough. The center of our galaxy, for example, is 20,000 light years away. Take 20,000 years for light itself to go from the center of our galaxy to us. And our galaxy is a nothing compared to the expanse of the whole universe. So how are you going to be going through the universe when you can't even get to your own galaxy? It's going to take you 20,000. It's not going to take you 20,000 years. If you're traveling at high speeds, you might get there in 5 minutes. And if you travel at the speed of light, how far away would it be? From a speed of light frame of reference, what's the distance between things? And remember Leon Russell used to sing that song, I'll love you in a place where there's no space and time. I'll love you forever, you're a friend of mine. A place where there's no space and time? That makes sense? How can there be no space? How about from a speed of light frame of reference? From a speed of light frame of reference, what's the length between one edge of the universe and the other when v is c? 0. From a speed of light frame of reference, there's no distance at all between the one side of the universe and the opposite. And from a speed of light frame of reference, how does the duration of time travel? It's frozen. No time, no space. Do you ever hear the Buddhist type say, everything, the universe, really is just a point in space? You say, gibberish! Gibberish? Maybe from one frame of reference, that's true. Think about that.